you all for coming to my presentation. So to give you a little bit of a background, what we'll be talking about, the sensor fusion algorithm that we developed is its goal is to perceive road users from a moving vehicle, and you can already assume that the application is mainly in self-driving cars. So we want to detect all the cars and pedestrians and other road users around the vehicle. And to that end, we'll use object detection and object tracking. And of course, we'll deploy these algorithms on multiple sensors. And we will need some sort of sensor fusion algorithm to make them work better. So the novelty of my work is the improved system performance, so that the improved tracking and detection of pedestrians in corner cases. And we'll see later what these corner cases are, but it's a really difficult problem in general, and it's basically these corner cases is what is stopping the deployment of autonomous or self-driving cars in the market today. So in the end, I'll show you some experiments that we did on a large-scale data set. There are some conclusions and outlook for the future. So just to give you an example, what the goal is, our vehicle here is in the middle and is equipped with multiple sensors like cameras, Lidar, radars, and other sensors. And here I show a three-dimensional rendering, which shows the point cloud captured by Lidar to just give you an idea of the environment. And the output of the algorithm, the perception system that we're developing, is the exact position, orientation, velocity, and the class of all road users. So here we see some parked vehicles to the side. This is a cyclist going in the other direction, and also there are some pedestrians here to the side. So this is really important for the later stages of map planning and collision avoidance. So the sensors that are specific to this task are mainly cameras, Lidar, and radar, and they all have their pros and cons. Here I've listed some typical attributes of these sensors, and you can see that not a single sensor can satisfy all of these tasks with the green. So some of them work well in some tasks, like ranging is very well done by Lidar and radar, but not so much by camera, and I'll not go into too much detail here. The interesting part to see is the corner cases. So all of these sensors, they underperform under different types of corner cases. And this is really important for us because when we do sensor fusion, we will use the one sensor that works well in one circumstance to improve the performance of the other sensors. So here I mentioned that cameras fail in a glare, darkness, or occlusion. So this basically means that the camera image is losing contrast or is becoming very noisy, and the object detection doesn't really pick up all the objects in the scene. And the Lidar really fails when you have atmospheric pollution, like dust, fog, or also glossy objects, like when you have rain and all the surfaces become wet, the Lidar signal gets lost and the point cloud becomes really sparse. Also, the radar has some fail cases where you have multipaths, reflections, and where you have low relative velocity to the object that you're detecting. So here are some examples of cameras mounted in the rear view mirror of a car, Lidars on top, and this is a radar unit in the bumper of a car. So what I mean by object detection, in the camera images, this basically means that for each object in the scene, the detector outputs a bounding box in 2 dimensions. So here we have 3 cameras looking forward and to the left, and also we have 3 cameras looking to the back. So it basically gives us like a surround view of the environment, but just in 2 dimensions. And object detection in Lidar data does the same. So basically based off the point cloud that is scanned around the vehicle, we run some algorithm that analyzes this point cloud and gives us bounding boxes around all these objects. These were the pedestrians from the last image here in front, and all the other objects. So the camera gives us good classification, but it doesn't give us ranging, and the Lidar gives us really good position in 3D, but really fails in classification in the distance where you don't have too many points. So of course, in order to improve the system, we'll apply some sort of sensor fusion. And there are two main tracks of sensor fusion. Early fusion, which basically takes the raw sensor streams of all sensors and then applies a joint processing algorithm on all of these sensor streams together. So here is a mock-up like a convolutional neural network architecture that basically reduces the information into a single decision, and then this decision is like a position of the object in the scene. So these are really simple to implement, and they can be trained end-to-end if you have enough data, and they give state-of-the-art accuracy. And this is really good if you want to participate in benchmarks and if you want to have good accuracies under normal conditions. But these are really sensitive to domain variations. What this means is that if some of these sensors starts to produce faulty data, for example, the camera, this will really break all your processing pipeline below, even though you're getting good data from the other sensors. Here I also listed intermediate fusion, which is, in our way, we see this as a subset of early fusion. And in late fusion, we have individual processing pipelines for each sensor, and then this results in good flexibility that we can use black box component, and it's really robust to sensor failures. So if one sensor fails, the system switches to the other sensors. In practice, this means that here I give you an example with a Lidar and 6 cameras sensor array. So on the Lidar, we run a center point object detector. This gives us a lot of candidate detections. So these detections, they are passed through a threshold. And the same does for the camera object detector. In each 6 views, we run a camera object detector, and then these candidates are passed through a threshold, and all the confident detections, then they are matched on by projecting onto the camera images. Matched objects. For matched objects, we will compute the joint likelihood of object existence, and based on these 2 parameters, we can do object tracking. So just to give you a visual example, here we have a detection of a pedestrian in a Lidar point cloud and a pedestrian in the camera. And the matching is just by simply projecting using the camera calibration matrices, and then we can compute the intersection of a union in pixel coordinates. So a good match means that intersection of a union score is high, close to 1, and if it's like 0.5, it's an average match, and a 4 match is anything close to 0. And the joint likelihood computation is, it's a standard Bayesian framework that does this. So we have hypothesis of an object at position X, and we have a positive hypothesis and a negative hypothesis, and we test this ratio given all the evidence, these are like the detection scores from the object detectors. And usually this is done by taking the logarithm, so then we have the sum. And the shape of these log likelihood ratio functions, they can be estimated from labeled data. So here I give some 2 examples for the center point and the image object detector that we use. And so this has a problem in corner cases where like a low light, where the camera object detection really fails. So here there are 2 pedestrians in the darkness, which are not really picked up by the camera. And also there is some clutter. But if we add the object detection from the Lidar, that we can see that the Lidar is really invariant to light condition. So these 2 objects are really detected. So what we propose is a cooperative fusion technique, which really is based on the late fusion principle. But we remove the thresholds here, and we use the strong or the confident detections from the Lidar and match them to weak evidence in the camera image. So exactly like we had here, these are confident Lidar detections, and there is like really weak evidence from the camera. And we boost these camera detections in these situations. So we increase the log likelihood ratio of the camera detectors. And after matching, we apply a threshold and track this object. So this is how the log likelihood ratio of the camera is implemented by using the intersection of a union with strong Lidar objects. So the benefits of this technique is, as I said, the confident Lidar detections, they lift the otherwise lost camera detections in areas of poor lighting or low contrast. So this means that we increase the recall at the same false positive rate. So we don't produce more clutter, but we pick up more objects from the camera. And because we implement this in a late fusion framework, basically the sensors, they remain their conditional independence. So we can apply all the Bayesian probabilistic reasoning later in the tracking. And it also retains all the benefits of late fusion, like the robustness to sensor failure. The downsides, because we remove the thresholds, now we have increased computational load for matching before we apply the threshold. So there are more objects from the lidar and the camera that needs to be matched. And also this boosting is context dependent. So here I only show you one example that we are using our knowledge that the lidar is much more accurate in dark conditions. And we use that to improve camera detections. But there are many contexts that in this cooperative fusion can help, which is really difficult to model, and this is more of a future work for us. So to test our idea, we employed experiments on a new scenes dataset, which is a large-scale autonomous driving dataset. It has 3D objects, 3D positions of objects labeled in the scene for, I think, 1,000 sequences, and it provides 6 camera views, long LiDAR, 5 radar data, and it's captured in two cities. In our experiments, we measure tracking metrics like MOTA, MOTP, and all these others, which I don't report here in the presentations. But this is basically the accuracy and the positional precision in the ground plane. And compared to 2 reference methods, the center track, which employs late fusion, and CBMOT, which also uses late fusion. So here I show you some results. The blue bars are our technique using cooperative fusion, and the red bars are our technique using late fusion on the camera and lidar object detection. And the other 2 bars are center track and CB modes, which are both late fusion techniques. So we can see that we outperform in AMOTA, we outperform also in MOTP, which is the positional precision on the ground plane. And we also recall more objects at the same precision. So in conclusion, we can consider this technique that we developed, that we allow that these cooperating sensors to adjust their detection thresholds locally using information from the other sensors. Compared to late fusion, we detect, as we saw, more objects at the same false positive rate, and also it's we measure tracking improvements, especially in corner cases, which I was not able due to time limits here to show you, but really at nighttime, the improvements are really significant. And for the future, we want to apply this feedback technique on multiple sensors. So we also have radar and also radar and camera direction. So we are looking into LiDAR and radar cooperation. And also we want to use deep learning to basically offload the modeling to a neural network instead of the equation that I proposed. So thanks for your attention. And if you have any questions, I'll be happy to answer you.